Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
University, and he's going to be talking to us today about a topic near and dear to my heart, abstraction, and he'll tell us a little bit about data abstraction. So, welcome.
Thank you, Tom. Okay, so the title of my talk is Data Abstraction Without Transition Abstraction, which in the interest of full disclosure, I should say, is not the title I sent around on my abstract. But I think this is a better fit for the ideas I want to talk about. So sorry about that. Before I get into the main content of my talk, I wanted to briefly outline the software model checking effort at BYU. There's two faculty, myself and Eric Mercer, 4 PhD students, Rohil Kumar, who's here as an intern now, and Tonga Bao, who's visiting with me today as well. And then Neha Rungta, who's working on heuristics for guided model checking. And I'll talk a little bit about how her work relates to these ideas in a minute. Her work isn't directly related to abstraction, so we'll kind of skip over that. And Kevin Simonson, who's working on disk-based and parallel methods for LTL model checking. And we have 3 master's students, Joel, Jertan, and Joseph, and 2 undergraduates as well. So I want to give a brief introduction to the idea of model checking, not so much to teach you what it is, but more to set up the terminology a little bit and set up some of the issues I want to talk about. So the model checking problem, the way I want to phrase it, is the problem, you're given 3 things. The first is a transition relation T, which given a state tells you what are the next states of the system under test, or next state. And an initial state S, which is just the initial state of the system, and a property P to be checked. And the goal of the problem of model checking then is to determine if the transition system, starting at state S, is a model of some property P that the transition system is supposed to satisfy. So in software model checking, the transition system T is defined by an interpretation of a program. So you're given a program text, let's say it's a C++ or a C program text, and you interpret that in a way that gives you a transition relation. And that transition relation is the thing that's going to be verified against some property for some given initial state. So one of the key ideas in software model checking is data abstraction. Data abstraction is important for 2 reasons. The first reason is that in some interpretations of program text, variables are allowed to range over the integers. So there's an infinite data space for the variables. And model checking over infinite data spaces introduces new problems with like decidability and representation. So it's nice to avoid that idea by using an abstraction that gets away from infinite data domains. Even if you do pretend that variables have a finite domain, then software model checking is still difficult, mostly because of a combinatorial explosion in the number of different variable values that need to be considered. So the idea then is to replace the domain, the original domain of the variables, with a smaller domain. And in predicate abstraction, the idea is to replace all the variables with predicates, which have a 2-valued domain, which is convenient. So the transition abstraction in model checking goes something like this. So each instruction in a program can be viewed as a single transition in this transition graph. So there's this transition system that one is trying to verify. And one way to look at software model checking is that each instruction is its own transition. So in a transition abstraction, which is often forced by a data abstraction, the idea is to replace each of the original transitions using whatever interpretation you wanted for your software with some transition over the abstract data variables that has either the same behavior or more behavior, so that you can end up saying something meaningful about your verification result in the end. And I'll go through an example that describes this in a little more detail. So the main idea that I want to get across in my talk is that being able to do data abstraction for software model checking without requiring a transition abstraction avoids a problem. And that problem is the problem of determining what a program actually means during the data abstraction phase. So the problem of determining what a program actually means, it's kind of a subtle, tricky problem in certain contexts, and I'll kind of get into that. But the main idea here is that we want to be able to do a data abstraction for software model checking, because that's absolutely essential for things like scalability and termination. But we want to avoid this problem of doing a transition abstraction. And now I'll go through an example that makes this idea, I hope, a little more precise. So here's a simple program. Excuse me. Here's a simple program that has one variable, x. We start by assigning x to a value. A little while loop here. So while x is less than this other value, which is about 2 billion and change, we increment x and continue through this while loop. So one way to abstract this program using a predicate abstraction is to pick a predicate, say q, and q simply asserts that x is less than this value. And then given this predicate, we rewrite the transitions of the program to create a new program, which I'll call P2. And in this new program, P2, each transition in the original program is replaced by a transition in the new program, such that the new transition, T prime, operates on the abstract variable. And here's the tricky part. This new transition, T prime, has the same effect on the truth values of Q as the transitions in T do, as the transitions do in P1. So this transition T prime has two properties, operates on the abstract values, and it computes the same effect on the truth values of the abstract values as the original transition does. And I'll briefly go through how that looks for this program. So the two interesting bits are right here, the guard and the while loop, and the instruction that increments x. So the guard on the while loop, conveniently enough, is just the predicate that I picked. So I can replace the guard on the while loop with just the truth value of the predicate. And then the way that this is read is that when I increment x over here, that has an effect on q. And this tuple means that if q is true going into this instruction, then the first value gives the value of q after this instruction. And the second value, on the other hand, if q is false going into this instruction, then the second value gives the value of q after the execution of incrementing x. So the way that works is that if q is true going into this instruction, then q is either true or false after x is incremented. Because q simply asserts that x is less than some value. If I increment x, it may or may not remain less than that value. On the other hand, if if x is greater than this value before I increment x, then x will continue to be greater. Now, I could have simplified this a little bit because I know that q is true when I come into this instruction, but I wanted to kind of get it all in one place. So that works fine. So what I've done is I've replaced these transitions with transitions over here that have the same effect on q as this transition would have on q. So here's another simple program. It's the same basic program, except this time I'm going to assert at the end that x is greater than 1. And I've added a couple new predicates. I'm setting this example up very carefully to create a problem, which you'll see in about 2 or 3 slides. So I've picked 3 predicates, same basic program with an assert statement at the end. If I interpret this program using unbounded integers as my model of how software works, then I'll get a Boolean program, or a program over these Boolean values that represent the truth values of these predicates that looks something like this. So the interesting bit here is what happens when x is incremented. So when x is incremented, q behaves as before. If r was true before x is incremented, that is, if x is greater than 0 before x was incremented, then it remains true afterwards. If r was false before x was incremented, then it may or may not be false afterwards. And similarly, s is true. If s was true before x was incremented, then it's true afterwards. And if s was false before x was incremented, then it simply takes on the value of r afterwards. So if we draw out the transition graphs for these two programs, then we get 2 transition graphs that look something like this, assuming we interpret the program over the unbounded set of integers. So x simply increments along till it reaches a value that violates this guard. We assert that x is greater than 1. This value is greater than 1, so the assertion passes. On the other hand, for the abstracted program with the abstract transitions, execution can kind of bounce around in this loop for a while. Eventually, it'll bounce over to this other value, and then eventually the assertion will pass. because I can't exit this loop until, so I have to, when I exit this loop, the value of s is always true. My assertion was just s, which is that x is greater than 1. So when I come out of this loop, the assertion always passes. So what I've done here is I've created an abstract version of this program that captures the meaning of this program under its interpretation over unbounded integers. The problem is that when I run this, when I interpret this program on, say, a processor with 32-bit signed integers, then the interpretation of the program is different. Because this value right here just happens to be maxent plus 1, which ends up in a signed 32-bit representation being negative maxent. So the while loop is actually never executed and the assertion fails at the end. So just in case you don't believe me, here it is on my laptop. So here's that program in C. So what I did is I wrote the limit down as maxent, and then I added 1 to it as a variable, so the compiler wouldn't warn me that I was about to exceed the maximum size of the variable, because I didn't want to see that warning. And I was trying to set up an example. All right, so then I do the while loop, do the assertion, and the assertion fails. So the point I'm trying to make here is that if a data abstraction requires a transition abstraction, which predicate abstraction does when done this way, then the transition abstraction has to be done. Then the transition abstraction is only as good as the interpretation that one takes of the software under test. So in this case, if I assumed that integers truly were unbounded, then my transition abstraction captures that fact, and integers behave as though they're unbounded. However, if I execute the program on, say, a 32-bit architecture with 32-bit signed integers, then my original interpretation of the program doesn't match the interpretation of the program on the hardware that I executed it on. So this is just a very simple example. I mean, there's lots of different ways you could avoid this problem that are really straightforward. But the point I'm trying to make is that interpretation and predicate abstraction is an important thing. So typically it's done using a C program text with a set of predicates and the C language definition, with the caveat that the integers are typically treated as unbounded. That's translated into a series of theorem prover calls, which eventually result in a Boolean program at the other end. Now, there's also an opportunity for transitions to be further mangled in these theorem prover calls. But that's just how theorem proving is, and that's OK. So in reality, the way the semantics work, and I put reality in quotes because I work at a university, and we never really deal with reality in the first place. So the way that it works in reality is somebody took the C language definition along with the target instruction set architecture definition and came up with a C compiler that hopefully preserves this definition under that definition. The C program text is given to the compiler. You get an executable, and then there's some behavior on a silicon processor. Ideally, the behavior of the instruction set architecture on the silicon processor is the same as the instruction set architecture definition that the C language that the compiler writer used. But you can see that there's lots of opportunities for the meaning of a program text to be different than the meaning of a program text as it was used in abstraction. So the goal of our work is to be able to do data abstraction, because that's a critical thing. But to do data and abstraction in a way that avoids the necessity of abstracting transitions. And here's 4 reasons why I think that's a good idea. The first is that it avoids the problem of understanding what the program transitions do in the first place. So if you want to stay close to the meaning of a program on an actual piece of hardware, it's actually a hard problem to know what a program transition does. Because, well, given a C program text. Because the compiler is going to introduce some new behavior. The actual behavior of the machine code on the processor might introduce some new behavior. And then if you throw concurrency in, it gets even more difficult. Because more often than not, well, I shouldn't say that. Because a single C instruction can be rendered as several machine code instructions. And if your processor allows interleaving at the machine code level, then C instructions are going to be interleaved in a way that's really hard to predict by just, well, that's somewhat difficult to predict by looking at the C program text alone. So by avoiding transition abstraction during the data abstraction phase, we avoid this whole problem of understanding what the transitions do. The other thing that's nice about avoiding transition abstraction is that we can deal with complex data operations. So if you're using a theorem prover to understand what your transitions do to the abstract variables, then you're sort of limited by what the theorem prover can do. So for example, if you want to do things like multiply variables and compare their values to each other, then you sort of stepped into an undecidable theorem proving problem. And your theorem proving will be less accurate, because it might be able to figure it out through constant propagation in some cases. But the theorem proving is not going to be able to support you as much as it could have otherwise. So by avoiding this transition abstraction step, we don't worry about the complexity of the data operations, because we just execute them with their real values, and it doesn't really matter.
But then you're doing under-approximation, not over-approximation. So fundamentally, I mean, the goal of transition abstraction is generally to provide an over-approximation of the underlying concrete semantics, right? So somehow you have a different goal in mind.
Yeah, so we took, there's two approaches to this problem that I'll talk about. The first is just a dead variable analysis that we performed during model checking. And that ends up giving us the exact transition relation that we started with. So we end up without any under-approximation at all, or over-approximation. On the other hand, if we do, the other abstraction technique is Karina Passerianu's predicate abstraction technique, and that does end up with an under-approximation in the end. But it's not predictable, but it's an under-approximation that you can measure and know how bad it was. Does that answer your question? I mean, is that kind of...
Yeah.
All right. We can come back to that. The other reason to avoid transition abstraction is that if you don't have to understand what the program actually does, then you can use the actual execution engine that's going to execute the program to tell you what the program actually does. And this is kind of the philosophy behind the Java PathFinder that came out of NASA. So rather than build a semantic model of Java programs, you just think, hey, I've got this Java virtual machine that's going to assign this semantics to my program. Why don't I just use that as the semantics for my program? And you can do that by instrumenting the Java virtual machine to act like a model checker. And we did that as well in a tool called Estes. Our tool, Estes, basically uses the GNU debugger. And we instrumented the GNU debugger to act like a model checker. So now we get the semantics of binary executables as interpreted by the GNU debugger. And so that avoids the whole problem of figuring out how machine code gets executed, how the interleaving is going to happen, and all that. And the other nice thing about avoiding transition abstraction is it sets up this really nice method of reasoning about software components that I'll get into at the end of my talk. So I kind of gave an introduction to this idea of data and transition abstraction and why we want to separate the two. The next thing I'll do is talk about a data abstraction that we developed that we call dynamic dead variable analysis. And then I'll talk about an idea for component abstraction based on this. So very briefly, one approach to model checking is explicit model checking. And explicit model checking, you have a queue of states that are waiting to be expanded under the transition relation, and a table of states that have already been visited or expanded. And a transition relation, which basically boils down to a function that, given a state, returns a set of states that are the successors for that state. So this is the successor relation. So in explicit model checking, one of the fundamental limiting factors is the number of states you can fit in this table of visited states. The reason you need a table of visited states is to avoid duplicate work and to detect termination. So this ends up just being a big giant hash table in memory that often exceeds memory. So the goal of data abstraction in this case is to make this table smaller. There's two main ways to make this table smaller. One is to put fewer states in it, and one is to make the states you put in it smaller. And this particular approach to data abstraction will do both. So typically you'd call dead variable analysis a live variable analysis, but we're focused on dead variables, so we call it a dead variable analysis. So dead variable analysis in model checking is a pretty simple analysis that has a positive impact. So it appears in these model checkers, Bogor, if, and spin. So the goal is to do a data and path abstraction without a transition abstraction. And the nice thing about this data abstraction is that the complexity of the underlying data operations is irrelevant, because we're going to do the data abstraction using actual values at runtime rather than using symbolic values before runtime. So we don't have to use a theorem prover or any other analysis technique to try to figure out what the data manipulations do. So briefly, a variable v is dead at a program point p if this temporal logic formula is satisfied. And that is that variable v at program point P is a model of this formula. And this formula says that along all paths starting at P, v is defined, releases the obligation for v not to be used in the future along that path, which is just a temporal logic way of saying that a variable is dead if it's either redefined before its next use or not used at all. So here's a variable v, here's a location P. It's redefined on this path before its next use. It's not defined at all along this path. So this variable is dead at this location. So one way that you could improve dead variable analysis is that instead of computing that, instead of determining whether or not a variable is dead over all paths through a control flow graph, you might want to determine whether or not a variable is dead along all feasible paths in a control flow graph under a given valuation of the program state. So you could improve dead variable analysis by checking it using this formula right here. And this formula says that a variable v is dead at program point P for variable valuation sigma if it is a model of this temporal logic formula. And this temporal logic formula says that along all paths that are feasible for this variable valuation, v is redefined before its next use or not used at all. So pictorially, here's what that looks like. Here's P, here's a variable valuation that assigns x to the value 20, and then assigns a bunch of values to the other variables that we don't really care about. The end of this basic block 2 here, has an if statement, and let's say that the guard on that if statement is that x is greater than 20. I'm sorry, that's 10. It says if x is greater than 10. So if x is greater than 10, we go down this branch, otherwise we go down this branch. So using this valuation-sensitive dead variable analysis at runtime, we can figure out that this branch is infeasible for this variable valuation. So although v is used along this branch is infeasible, so we can ignore it. This is the only feasible branch, and v is not used along that branch. I'm sorry, it's defined before it's used along that branch. So v is dead under that variable valuation. It's a pretty straightforward idea. So that gives rise to a model checking algorithm that looks something like this. Start off by doing a dead variable analysis to get what we can for all paths, not just the feasible ones. Start model checking every now and then. And it turns out that really getting precise about what we mean by every now and then is an interesting problem. But every now and then we stop model checking, run a forward simulation using the current valuation of all the variables in the program to prune the control flow graph, and then run a dead variable analysis on the pruned control flow graph, and then repeat at step 2. So the idea is that in step 5, we can mark more variables dead, store less stuff in the table of visited states, and explore fewer paths through the program. So there's 2 main problems with that algorithm as I presented it. The first is that merging incomplete forward simulation information with backward analysis starting at the exit is a little tricky, and I'll talk about that in a second. The other is that dead variable analysis information is now valuation sensitive. So rather than statically annotating the control flow graph with the sets of dead variables for every basic block, the sets of dead variables for each basic block now change depending on the valuation of the program variables. So it's not that hard to manage that information, but it's a trickier problem to manage it efficiently in a way that doesn't significantly slow model checking. I'm going to skip over that part of the algorithm, but I'll talk about that part. So the first issue is merging the depth first search information, which is how we do the forward simulation, with the variables in the current program valuation, and the dead variable analysis. So here's a little example of how that works. So let's say we're in basic block 1 and decide to stop model checking and do a forward simulation to prune the control flow graph. Now in this forward simulation to prune the control flow graph, there's a bit of an engineering decision which needs to be made about how far to do this forward simulation. So on the one hand, it could be done all the way to the exit, and we could get the most pruning. On the other hand, it could be done one step and get the least pruning, but be the fastest. So we set that up as a parameter to our system and kind of played with it to see what would happen. And it turns out that the problem of determining how far to go in forward simulation is a little more subtle than we had first anticipated. So let's pretend we go from basic block 1 to basic block 5 during forward simulation. And we're able to figure out that only this branch is feasible, that branch is not feasible. So the problem is that a standard dead variable analysis would start at the exit point and is a backwards data flow analysis. So it would proceed backwards through the control flow graph to figure out which variables are dead along which paths through the control flow graph. Unfortunately, our forward simulation didn't make it all the way to the exit. So we need a way to merge the information about which branches were taken during the current program evaluation and which branches must be taken to make each part of the control flow graph reachable. So the way we did that is before model checking, we perform a data flow analysis with a bit vector. And that bit vector has a single bit for every branch in the program. And we compute a fixed point on the outcome of each conditional and how it affects the reachability of each block. So for example, block 3 here is reachable only if branch 2 evaluates to true, and block 5 is reachable only if branch 2 evaluates to true. Similarly for block 7. Block 9 is reachable, and it doesn't really matter which outcome we had for branch 2, and it doesn't really matter what the outcome was for the branch at basic block 6 either. So you can see that since there's a loop over here, it really doesn't matter what the outcome is for at the end of basic block 6 because each of these 3 blocks are ultimately reachable for each outcome of that branch. So it's a pretty straightforward data flow analysis to try to figure out which branches affect the reachability of which basic block.
Isn't that more just a control dependence analysis?
Maybe. So tell me why. Yeah.
Control dependence generally says which predicates govern the execution of which blocks.
Yeah. Yeah, let's talk about that offline. So the way I came up with data dependence analysis was I pulled my favorite compiler's book out after we designed our analysis algorithm and said, what does that look the most like? Mm-hmm. So yeah, I could go.
Yeah, no, you can encode control dependence as a data flow analysis, but there are much more efficient ways to do it.
We should talk about that offline because that would be interesting. So then during model checking, we keep track of which branches actually were taken given the current program evaluation. So I'm at Microsoft. How do I make that go away?
What is it?
I don't know.
Your pen?
I'll just kind of tuck it away right there. All right, good. So, sorry about that. So what we do is during dead variable analysis, we check the decisions that must be made to reach a basic block against the decisions that were made during forward simulation to prune out paths. And in this particular figure, the decisions that must be made are shown in black, and the decisions that were made are shown in blue. And the evolution of the backwards analysis for dead variable analysis is shown in green. So basically, going from 10 to 9, the outcome of 2 doesn't matter. Using this particular program evaluation, the branch at the end of basic block 2 ended in true, which is consistent with doesn't matter, so the analysis proceeds. Along this branch, the outcome of the branch at the end of basic block 2 must be false to reach this basic block. The outcome of the branch at 2 was true, so this branch can be pruned. However, along this branch, it's consistent, so it marches all the way up to the top. And only this part of the control flow graph is considered in the dead variable analysis. So really, the pruning of the control flow graph and the merging of the information from the forward simulation is all done on the fly, and it's just kind of a one-pass thing through the control flow graph. So the second algorithm looks something like this. The first thing we do is go through and do this analysis to annotate the basic blocks with branch outcomes. Then we do a standard dead variable analysis to mark the stuff that's always dead. Start model checking, every now and then stop. When we stop, we do a forward simulation to collect branch outcomes. And we run a static dead variable analysis algorithm while pruning the control flow graph based on those branch algorithms. And then we go back to step 2 using our enriched set of dead variables, and things work out well. The details about how we manage the valuation-sensitive dead variable information is in our paper at PEPM from January of this year. The punchline is that it's really efficient and cool and only uses memory when it has to and frees memory whenever it can. So we coded this thing up. When I say we, I mean Michael Lewis, who's recently hired into the Office group. So we coded this thing up in our Estes model checker. Estes is a machine code model checker. It uses explicit state enumeration with GDB to evaluate programs, which, like I was saying before, saves us the trouble of understanding what binary programs do at all. It requires an environment model provided by the user for off-chip inputs. So we set GDB up, we set Estes up initially for embedded processors. So we used a small Motorola processor for all of these results. The one caveat about our algorithm that you might not have expected is that our dynamic dead variable analysis during verification actually gives up at points of non-determinism. And the reason it gives up at points of non-determinism is because then we would have to save and reason about branches of reachable path information rather than straight line flows of reachable path information, which clutters up the algorithm a little bit. I don't think it would be a difficult extension to deal with trees of feasible branches rather than just straight line path. So we tested this idea out on 4 different programs. These are the 4 programs. I'll talk about more of them more in a second. They were written in C. We compiled them with the GCC compiler for the Motorola 6811. And our objective here was to compare dynamic dead variable analysis for model checking with this standard static dead variable analysis for model checking. We wanted to see what the time-space overhead of our technique was. If we actually marked more variables dead, if we explored fewer states, and if we actually saved any space in the size of that table of visited states. So here's the results. Dining philosophers is surprisingly dining philosophers. The way we implemented it, it had 1 loop and no pointers. The reason I mention on each one of these programs kind of what the pointers looked like is because in a static dead variable analysis, pointers are a little tricky to deal with because it's not exactly clear at static analysis time what the pointers are pointing to. So you kind of have to pretend it's either the whole working set of the program or all of memory or just the memory you can get to without an access violation. But during execution time, all those pointers can be disambiguated, so you can get a lot of a bit more pruning out of the analysis. So this dining philosophers problem was kind of not a good problem for dynamic dead variable analysis because it has no pointers. So you can see that the top line is model checking this problem with no data abstraction through static or dead variable analysis, static or dynamic dead variable analysis. It takes about a second to verify it, explore 7,722 states, hash tables that big. This overlay size measures how much extra memory the dynamic dead variable analysis needed to store these valuation-sensitive dead variable sets. So the thing here is that dynamic dead variable analysis saved no time, saved no memory, and cost no memory. It actually cost some time, but that's the way it goes.
What's the distinction?
Oh, thank you, Rahul. Sorry about that. The distinction is that there's a lot of different parameters to a dynamic dead variable analysis. One of the things we did is we set it up so that the amount of forward simulation we did could be controlled by a parameter. And so we tried 14 different combinations of the parameters. This was the one that ran the fastest, and this was the one that ran the slowest. So rather than increasing the length of this table by 56, we just reported 2. Actually, it would be 38, I guess, because we already have 2 lines per. All right, so that's dining philosophers. This was kind of a nice example of something where our analysis got no reduction, did nothing useful. All it did was cost time, and it kind of almost doubled the running time, which wasn't great, but it didn't cost us any more memory. And explicit model checking memory is really the main problem. The good people at Intel will help us solve the time problem every chip release. So Bulls and Cows is a little game. It's a 1-player game. It has 3 loops and a few pointers. So you can see that we're getting a little bit of reduction here. So we took the hash table size down from 211 kilobytes to 209, which is maybe not something to really write home about. but it's a small problem anyway, so a small reduction on a small problem is fairly reasonable. And it cost us 0.14 kilobytes in overhead to keep track of our valuation-sensitive dead variables. And you can see that the running time came down a little bit, but not a lot. Timed SSE is it's an interrupt-driven program that updates variables. We also had to deal with variable uses and definition and interrupts, and I'll kind of skip over that, but that's in the paper as well. And we got a little bit more reduction. Things are starting to look better there. Though, what we did is we designed the program that's the ideal program for this kind of analysis. And here's what it looks like. So this is a control flow graph. These are basic blocks. We have 8 variables, x1, x2, and x8, that are defined in this basic block. And each basic block ends in a guard of the form x5 times x6 is less than x7 times x8. And then at this level, the basic blocks end in a conditional of the form x7 is less than x8. And then at the lowest level, each basic block includes a single use of each variable. So at compile time, it's difficult to figure out which variables are actually going to get used in any of these paths down to exit. But during execution time, it's pretty straightforward to evaluate the outcomes of all those multiplications and prune the control flow graph down to a single path. So now we can mark 7 out of 8 variables dead and get a nice reduction in the state space of the program. And we can make that reduction arbitrarily large by increasing the range of the variables. We didn't play that game a lot, but we could have. We could have made ourselves look even better. So the nice thing about this result is that this result says that in the ideal case, we actually got the reduction we were expecting. In these non-ideal cases, we kind of got meager results. So the nice thing here is that the hash table size went down from 52 kilobytes to 13 kilobytes in the best case. The running time went down by 1/3, and the number of states explored went down by about a factor of 3 as well. The reason for that is that if all the variables are live along this path, then we have to explore this path for each value of all of the live variables. However, if we mark all of the variables dead, well, if we mark more of the variables dead, then we have to explore this path fewer times. And that's exactly what we observed in the execution of the program. I'm going to skip that slide. So the summary of this part of the talk is that what we set out to do is create a data abstraction for arbitrarily complex transitions. That is, anything you can evaluate with GDB, we can shove through this, is OK under this data abstraction. We use GDB to provide the program semantics, which is convenient because it includes all the warts that the implementation of the ISA includes, and all that funky stuff that the compiler does ends up being in our semantic model for the software we're verifying. And if you're actually going to run the software, then you care about things like that. It works well for certain program structures. So the deal is that if your program looks like something like that, then this is probably a good analysis. If it doesn't, then this isn't so useful. So the next step in the work is to design heuristics that analyze the control flow graph before model checking time and figure out when to do this analysis and when not to do this analysis.
So your forward simulation is actually concrete execution?
That's correct.
So, I mean, how, but in your example, you were saying that, you were proving that some branch was always true.
Sure.
So, I guess since you're doing it with concrete I'm not clear how you're doing that without the use of a theorem prover.
Oh, yeah.
Because you basically, you see some execution and it takes the branch. It always takes the branch true, but maybe there's some other input that makes the branch go false. So it wasn't clear to me.
Sure.
What.
So there's 2 issues there. The first one is that when I have my program and I'm in this state, let me get a different color. It's going to be. So when I'm right here in execution, I know all the values for all these variables.
Sure, right.
So actually evaluating this guard, you just send it off to the processor and it gives you back.
Right.
Yeah, okay, good. So then the thing is that when I've evaluated this guard for these values and pruned my control flow graph for these values, so let's say maybe only this part is reachable, that's all I know. If I have a different set of values later on, and I reach this basic block again with a different set of values, I have to redo all of that. It's like a very narrow theorem-proving result. So it's a theorem-proving result that tells me the branching structure of my program for a single valuation of the variables. So if I want to do that symbolically for like lots of valuations of the variables, then I'll need a theorem prover step, and then I'll need to...
I see. So really it's like when you're saying dead variable analysis, it's very conditional. It's not just conditional symbolically, it's conditional on particular input.
That's exactly right. And so that's the second problem with this work, is that now all of our dead variable information is sensitive to the variable valuations that you gave.
I understand, but if that path was like a hot path or something, and you were doing compiler optimization, you're basically in the world of doing, a dynamic data flow analysis on the hot path of your program, which people do. So it's not. The question is, what are you using the result of your analysis for? And if you're going to do code duplication in compiler optimization, you can split out that path and you can take care of you can do super block optimizations or what have you. So it's
And specialization.
and specialization.
Yeah, all we're using it for is to avoid sticking stuff in the hash table. So we're not emitting code at the end or anything.
No,
It's just,
I see.
you get that.
I guess I was just so in the beginning, sort of you talked about model checking and the problem of transitions, and so I was a little confused because I was thinking about proving properties, and here in this with this forward simulation, which is concrete execution, you're not getting a proof for all paths. You're getting precise data flow information along say a hot path, and so I just had a disconnect between the first part and the second.
Good. Any other questions? All right, great. So one of the problems with the way that I should mention this. So the overall philosophy in this particular piece of work, from an analysis point of view, is to take an idea from static analysis that you might use in a compiler and adapt it to the situation that one finds oneself in model checking. So in model checking, the actual model checking of a piece of software is so costly and so computationally costly that sort of an expensive analysis like this actually makes sense and saves time in the long run. And so we took a similar approach to guided model checking. So in guided model checking, you have this control flow graph, and certain parts of the control flow graph contain assertions where the properties that you're trying to check might fail. So the idea is to drive the execution of the model checker towards those basic blocks so that you can check the assertions more often and more quickly. And the way that that's been done is to do shortest distance functions over the control flow graph to say, if I'm at this basic block and I want to be at this basic block, what's the shortest path to reach that other basic block? That's a little bit difficult because you have to disambiguate function call returns. You have to deal with pointers and things like that. So we took a similar approach where we would prune the control flow graph during model checking and then do the shortest path analysis. And that heuristic has gotten some nice improvements over other heuristics for guided model checking. And that's Neha Rumta's work. And our future work is to get all the dead variables for a given valuation. And basically, this forward simulation, which I think a better name for it would just be concrete execution. So this concrete execution step, in model checking, in retrospect, there's no reason to do that only partially the way to exit, because in model checking, we're going to do it all the way to the exit anyway. So in that, when we stop model checking and do this concrete execution to print the control flow graph, we might as well go all the way to the exit, save the program states we got, and then just replay them again when we model check all the way to the exit using concrete execution. And so it turns out if you play the game that way, then you can get all of the dead variables for a given valuation. And if you play some games with how you manage the information, you can make it even more efficient. And that's what Joel Self is doing for his master's thesis. All right, so I kind of want to switch gears a little bit and talk about an idea for component abstraction that builds on the idea of data abstraction without transition abstraction. So the idea is that we have an abstract component inside of a concrete piece of software. So rather than taking a component and verifying it, well, I'll just flip to the next slide. So rather than the typical approach is to take some software that surrounds a component and abstract it and create an environment which over-approximates the actual surrounding software. And then to verify some concrete software component inside that abstract surrounding environment. And the whole software artifact is usually embedded in an abstract execution environment, which describes like what a user is going to give it or what some other system is going to give it. So we're thinking it would be a good idea to abstract the software component and leave the surrounding software concrete. And the reason that's a good idea is because let's say that the software system one is trying to verify is, say, the transaction manager in JBoss. So the transaction manager is sufficiently complicated that a data abstraction is a good idea there. And the surrounding software is sufficiently complicated that abstracting it's going to be a difficult problem. So the idea is to leave it concrete and then deal with the software inside of it abstractly. And that's easier to do if the data abstraction for this software component doesn't change the transition relation. Because then when a state progresses outside of the software component and we have to see what the surrounding software is going to do with a particular program state, if the abstracted software component is dealing with the concrete transition relation anyway, then the pass-off of verification over this boundary is a little simpler. I'll describe that in more detail in a second. So the thing that makes this work is an abstraction that Karina Pasarianu published in CAV last year. And her idea goes something like this. You use the concrete transition relation, so there's no transition abstraction. And she uses an abstract state matching, which basically looks like hash compaction in model checking, except instead of using a hash function, so a hash compaction, you take a big program state, hash it down to a smaller value, and then store that value as the representation of that state. If more than one state's hashed to the same value, then they just collide in the hash table. You miss some behaviors, and you get an under-approximation like Tom was talking about. So Karina's idea was, well, rather than using a hash function that's just like dealing with bits and numbers and bit patterns, why don't we use a set of predicates to abstract the states and then store a bit vector in the hash table that represents the truth values of those predicates over the state vector. So it's a little bit more of a semantically aware compression scheme. And if you connect it with a theorem prover, you can do things like you can determine when two states collided in a way that misses behavior. And she has a paper about it in CAV this year, like I was saying. So the way that works is here's a little program, looks like before, except I didn't play games with the guard of the while loop. If you abstract that with this predicate, x is greater than 0, then you get a concrete trace that looks like this. The way I've drawn this is that the number on the left side of the colon is the program location, and the number on the right side is the value of x. So the program just marches along, merrily incrementing x. Under this particular abstraction scheme, there's only a single predicate, so I've written the program location along with the predicate value. So the program marches along. In program location 1, x is initially, the predicate p is initially false, still false in location 2 because it's just an evaluation of a guard. Becomes true in location 3, still true when we come back to location 2. I increment x again. Incrementing x when x is already greater than 0 leaves x greater than 0, which means that the predicate p is still satisfied. So the way that the abstraction scheme works is that I'm now back in program location 3 with predicate p evaluating to true. And I've already seen that state before, so I'm done. So I actually miss all the rest of the behaviors of the program as x continues to be incremented. So rather than using predicates to create an over-approximation of the state space, you end up with an under-approximation of the state space. And that's not really like a feature of this abstraction scheme. The feature of this abstraction scheme is that you don't have to abstract the transitions in the program under test. In fact, you can connect this up with our Estes model checker and use GDB to provide the semantics of the program under test. And still do a predicate-based data abstraction scheme, which I think is really cool. But then, so for this component abstraction idea, so we have an abstract software component with an abstract transition relation, if you were to abstract the transition relation. This is a program state. This is it meandering through the abstracted software component. And when verification reaches the boundary between abstract and concrete, there's a bit of an issue here because this program state is just a list of predicates and their valuation. those predicates and their valuations may correspond to multiple concrete program states that need to be given to the concrete surrounding software. So for example, other parts of JBoss don't know how to execute on predicates. They just execute on concrete data values. And there's a large set of concrete data values that might satisfy a given set of predicates. All those need to be sent through the surrounding software, and there's a bit of a complexity explosion there. So if the transition relation is not abstracted, so now I have an abstract software component with a concrete transition relation, then here's my abstract state. It kind of meanders through the component. When it reaches a boundary, let me back up. Here's a concrete state because I'm executing concrete states on the concrete transition relation. And when I store them in my table of visited states, I abstract them first. So that's a bit of a, sorry about that. So here's my concrete state meandering through the abstract software component. When I reach the surrounding software, I have a concrete state that's being executed by the concrete transition relation. So I just pass it off to the surrounding software and nothing happens. So it works out pretty slick. So eventually, execution meanders through the surrounding software back to the abstracted component. I see a new concrete state inside the component. I run it through the abstraction function, check to see if I've seen it as an abstract state before. If I have, then execution stops. Otherwise, execution continues to meander through the component. So it's a way of doing a predicate-based abstraction scheme on a component inside the surrounding software that we think will give a component-based abstraction that will scale to large software artifacts. Because I only have to mess with the, well, I don't have to even abstract the transition relation of the component I want to verify. And I don't have to abstract the surrounding software, which is good when the surrounding software is, say, 20 or 30 files full of Java classes.
So you're only saving states for the blue area, right?
That's right. The red, I guess that's orange. The orange area you just kind of execute through. Which is good because JBoss is supposed to run fast, right? So when model checking goes through the orange area, it's just executing Java without anything. So I can't really say, one of the drawbacks of this approach, though, is that I can't really say anything about errors that are caused by behaviors of the surrounding software, because I haven't really kept track of the behavior of the surrounding software. So if I do find an error inside the component that I'm trying to verify, error trace generation is going to be a little tricky because I haven't really kept track of the trace through here. Unless I do, so now I'm going to think about how I'm going to keep track of the trace through here, how much of it I'm going to store, things like that.
Well, and then you also have to reverse your abstraction if you wanted to generate a trace.
That's true. But if I did a depth-first search, I would need to keep concrete states on the queue of states waiting to be expanded. And so I could just unwind that. I'm sorry, stack. That I could just unwind that stack. So, so what we're thinking is that data abstraction without transition abstraction can complement normal predicate abstraction. Gives us a way of dealing with complex data operations because we don't have to understand what transitions do in the first place. And we think it gives an interesting way to verify components in complex software. This work right here that I just talked about, components in complex software, this is work under progress. So, you know, this is just an idea that we're thinking about and pursuing. So this is the work that we're currently working on. Here's my contact information. And that's the end of my talk. If there's any questions, I'll be happy to take them. Rahul?
I actually have a comment about the dynamic dead variable.
Sure.
While you were talking, I just realized that if you were to always do your forward execution step, like even if you don't do it all the way, if you only did it for a complete branch,
Mm-hmm.
that may also produce enough results so that you have some improvement. Instead of saying 5 steps and you're in the middle of a branch and you stop your execution.
So you mean all the way to the end of a basic block?
Yeah, exactly. So
Sure. So I don't understand. So you're saying that rather than just doing the forward simulation or the concrete execution to an arbitrary point in the program, you just do it till you reach the end of a basic block, and that
yeah,
might.
you always do it for your basic blocks,
Hmm.
and then you abstract on your, and then you can do an abstraction on your basic blocks to create super blocks as well.
Sure. Interesting. I'm not sure how super blocks would be an advantage in model checking. But that was meant to be a question for you guys.
Well, so we're.
But we can talk about that offline.
Yeah.
Yeah. Any other questions? Okay. Thank you.